So taking a look at this meme, this building is a periodic table. And the question is, what room are they meeting in? And you can only figure it out based on the electron configuration. Now, to be fair, this is not simple because ions can have the same electron configuration despite being different elements. Yeah? Something like calcium 2 plus is the same as argon, is the same as chlorine minus. Those all have the same electron configuration. So we could take a stab at the most likely element here, assuming it's neutral. But if there's any charges in there, we could be wrong. And Lizzie got it. Her tip was go to the very last piece of the electron configuration and figure out where that places you on the periodic table. Does it place you on the 4th row? Hydrogen, lithium, sodium, potassium. It puts you on the 5th row because that's where we start filling the 4d orbitals after the 5s. So 5s tells you to come look at the 5th row. Then we look at 4d. Looking at just the last piece, though, will throw you off. Because zinc and copper, cadmium and silver, mercury and gold, they actually all have the same ending. 3d10, 4d10, 5d10. Because remember, it's more stable for the electrons to have completely half-filled shells or completely filled shells. So, all of these, these atoms, copper, silver, and gold, they half-fill their 5s. And instead, fully fill their 4d, rather than fully filling 5s and leaving 4d mostly fully filled. It's not as stable. So that was a good tip to get you in the region, and then make sure that you're checking everything before it so that you're not being thrown off by any anomalous ones. That's pretty cool, right?
What's the 11?
It's not an 11. That's a good question. It's actually just the quotation marks.
I was very confused. What?
4D 1011. Yeah. Now that is confused. I had the same thought, but it doesn't look quite like the ones. It's missing the serif on the top. All right. Now, to give us some exercise with the concepts we were finishing up yesterday. I say yesterday and tomorrow like we meet every day. But, you know, the yesterday that we met. Can you take these sets of atoms and can you rank them from smallest atomic radius to largest atomic radius? Take about 30 seconds to a minute. Copy them down, figure out where they are on the periodic table, and figure out how to rank them. Yeah, let's go smallest radius to largest radius. Smallest atom to largest atom. I made a mistake. I'm so sorry. Like the silliest mistake. I don't want sodium and magnesium. I actually wanted potassium and calcium.
What about the double chlorine?
Double chlorine? Those are two different sets. Sorry. So this is a set you're ranking.
Oh.
I apologize. That was not entirely clear. Can you rank these four? Not all of them.
I was like, all right.
Good question. I mean, that wouldn't have been a terrible question to do, but was not my goal. So in case you missed it, I changed sodium and magnesium to calcium and potassium. Now turn in with one another. Because at this point you should have recognized what these have in common and what is maybe different. Turn in with one another and see if you agree. How can you rank their sizes?
And then I would say. Oh, I love that.
I still do. What always throws me off is that June and July both have 31 days. Sometimes I like try to count in anyway.
I learned about this just last year, and I was like, where was this? This is so easy.
That was in 5th grade in Wisconsin. I don't know about you.
Yeah. Sorry.
So you recognize these two are not families in the row. And then the last one. All right, guys, what did you find? What is common or what's similar? What's the relationship between the 4 atoms in this first set? They're in the same, not group, period. Yeah. They're in the same row. That means that as we move further to the right, further to the noble gases, we're going to find that the effective nuclear charge increases or decreases. The effective nuclear charge increases. All of these atoms have the same amount of core electrons. Those core electrons are shielding the electromagnetic pull of the protons. But since they're all being shielded the same amount, more protons in the nucleus means a stronger pull on the valence electrons. Can you tell me what is the effective nuclear charge of silicon? 4. What is the calculation? Subtract. Other way around. Atomic number of protons, minus the core electrons. So number of protons in silicon. 14. How do you know that? It's the number in that block. It's number 14 minus how many core electrons for silicon? 10. And how do you calculate that? Did you count all of the elements leading up?
It's on the 4th row. So I know there's 4 valence electrons. I did 14 minus 10.
You know that silicon, neutral, has a total of 14 electrons. and it's in group 4, so it has 4 valence electrons. That means all the rest are core electrons. 14 total minus the 4 valence, that gives me 10 core. So Jordan, you second guessed yourself. This has an effective nuclear charge of 4. Phosphorus, 5. Because remember, the number of core electrons, not changing, but the number of protons is. Sulfur, 6. Chlorine, 7. Which of these has the strongest effective charge in its nucleus? Chlorine. So chlorine pulls on the atoms the most. Chlorine pulls on the electrons the most, shrinks down its shell. So this is larger than phosphorus, larger than sulfur, larger than chlorine. What is the effective nuclear charge of potassium? No, I don't think it should be 18. The effective nuclear charge, so rather than doing the calculation, the effective nuclear charge of potassium is 1. Compare that to calcium. Did you say 19 minus 18? Shouldn't it be 20 minus 18? It's the calcium, that's how we got this, 19 minus 18. Oh, okay. Calcium is 2, effective nuclear charge of 2. What about scandium, Sc? How many valence electrons for scandium? 3. Remember that in main group elements, which is p block and s block, you only count valence electrons as s and p electrons. But in these transition metals, you count s, d, and f. Transition metals won't have p valence electrons. So scandium, we count the 2 electrons in the s block and the 1 electron in the d block. That's 3 valence electrons. And this has 21 total electrons, 21 proton number, so 21 minus 18. Again, it leaves us with that 3. It's still just increasing. Titanium, 4. Okay, so what is the size gradient? Is potassium the largest or the smallest? It's the biggest. It has the least pull on its valence electrons. Largest atom to smallest atom. All right, what do you find about our halogen family? Yeah, so is fluorine the smallest in the family or the largest? It's the smallest. But what about the effective nuclear charge? What's the effective nuclear charge of fluorine? Why don't we do this? What's the effective nuclear charge of chlorine? 7. And because these are in a family, Ryan's got it, they all have the same effective nuclear charge. So how am I able to say that fluorine is the smallest, iodine is the largest, if they all have the same effective nuclear charge? It's the lowest on the periodic table, that's true. It has the most protons, but protons don't make up the atom size. It's the electron cloud that makes up the atom's size. It's got electrons. It's got all those extra electrons in larger and larger shells. Effective nuclear charge does not help you rank atoms in a family. Effective nuclear charge only helps you rank atoms in a period. Deal? Any questions on that before we move on? All right. Good practice. Now, moving from this covalent radius, or the size of a neutral atom, we want to look at the ionic radius. And as you can imagine, determining an ionic radius is a lot harder because ions will always pair next to different ions. So you can't just say, look at the space between the ions, measure their distance and divide it by 2, because one ion might be much larger and the other much smaller. You can't use the same principle as the covalent radius. So instead we'll say, based on the covalent radius, or relative to the covalent radius, and then we're going to have two outcomes. Anions are larger than their neutral atom. And cations have a smaller size than their atom. Are you guys okay with me just saying atom? Do you know what I'm saying? The neutral species, not the ionic species. Atoms are neutral, ions have charges. As you take an atom and you make it anionic, are you making it more positive or more negative? More negative. Cationic, more positive or more negative? Cation, positive. So can you rationalize this trend, somebody? Sarah. More electrons. Same number of protons, pulling on a larger number of electrons. I mean, you're basically decreasing its effective nuclear charge. And why is the cation smaller? Less electrons, same number of protons, greater effective nuclear charge. We're not going to calculate effective nuclear charge here. We're just going to recognize these trends. So let's just do a couple of examples, shall we? The chlorine atom versus the chloride ion. The potassium atom versus the potassium ion. Iron atom versus iron 2 plus versus iron 3 plus. Take a minute. Predict which of these you think is a smaller species, which of them is a larger species. Again, not comparing all of them, just the sets. Once you feel like you've got it, check with people around you.
Yeah, left, right, right. Sorry. Left, right, right. It's October.
What'd you get? Chlorine versus chloride. What's smaller? Chlorine is smaller. Same number of protons. Chloride has more electrons. It can't pull on all of those electrons the same. Chlorine is smaller than chloride. Potassium atom versus potassium ion. Which one is smaller? Potassium ion, because there are less electrons for the same number of protons. And what about this series of iron atoms? What is the smallest iron? The 3+ is the smallest because it has the same number of protons for the least amount of electrons versus iron reduced, iron 0, elemental iron, being the largest, having the most electrons to have to pull on with its protons. Great. This is where we introduce a term, the isoelectronic species. There are not a lot of things in chemistry that are very well named, but this is very well named. Isoelectronic, meaning they all have the same number of electrons. So, a question here, chlorine and chloride, are those isoelectronic with each other? No, they have a different number of electrons. Fe and Fe2+ and Fe3+, isoelectronic? No. But if I were to say Fe and Fe, those are isoelectronic. Or if I were to say Fe2+ and chromium neutral, those are isoelectronic because chromium 2+ loses 2 electrons to become just like chromium in a neutral state. So, let's compare how these isoelectronic species compare in size. Let's take fluoride ion, the neon atom, and the sodium ion. Notice how fluoride ion takes 1 electron and has 10. Neon has 10. Sodium ion loses 1 electron to have 10. All of these have 10 electrons. Which of them is the smallest? Chat with the people nearby you. See what you think, how the sizes change here. How many electrons in this isoelectronic series? 18. The easiest way to look here is just find chlorine, because then you just need to add 1 electron. Sulfur is just 2 electrons, phosphorus 3. Chlorine has 17 electrons, chloride has 18 electrons. These 3 ions are all isoelectronic to what neutral species? argon. They're all isoelectronic to argon. As well as the potassium plus ion, the calcium 2+ ion. How would you rank this isoelectronic series? They're already in order from biggest to smallest? Chat with each other, see if you guys agree. Are they already in order? How can you prove it? What would you say? No. The nucleus? But not the nucleus. Yeah. Correct. Yes. Because you are now limiting the number of protons in addition to increasing the number of electrons.
Okay, thank you.
Huh?
You made me doubt so hard.
I just wanted you to feel so confident that you could say it in words.
I could say it in words and still have -60 confidence.
That's something you can work on. Okay, what'd you find on this top series? What's your prediction? What is the largest atom or species?
We said fluorine is the largest.
You'd expect fluorine to be the largest because it is both the anion, so it should be larger than you'd expect it to be. And sodium, a cation, should be smaller than it already is. And they all have the same number of electrons. So they should be pulling on the same number of electrons, just with a different number of protons. Sodium is pulling on the same number of electrons with the most protons. Fluorine pulling on the same number of electrons with the least. Did you use that same rationale here? Same number of electrons. Just a different number of protons pulling. This has the most protons per electrons. This has the least protons per electrons. So that P3- should be the largest, chlorine minus the smallest. Now I want to show you guys this, this idea, because I agree with you. Based on our trends and our reasoning here, we should say sodium is the smallest, fluoride should be the largest. But let's take a look at this graphic that shows sometimes our trends do not go the way that we want them to go. Sorry. There we go. Here is sodium plus, fluoride minus. And what do you notice? Here's the, actually I don't know which number is which. I think that's the original size on the left and the ionic size. Oh, well that is good. I apologize. When you look at that, what do you see? Which one is larger, Na plus or F minus? You think F minus looks larger on that graphic? Am I just looking at it wrong?
It says 192.
Don't look at the numbers, just look at the size. What's the vibe? What looks larger? Sodium plus or F minus? Oh, I think I understand. This graphic didn't make sense to me. Now I understand it. I apologize. I thought I understood this graphic. I didn't. Do you know what this ball is inside of this ball? It's the electron cloud of what? What, you're saying what? This is the electron cloud of Na+. This is the electron cloud of Na. And this is the electron cloud of F. And this is the electron cloud of F minus. I misinterpreted that. I did. So if you read this the way that I did, you're looking at that gray shell of sodium being larger than even the orange shell of fluorine. That's what I was looking at. So maybe now that we understand it better, is the teal of Na plus larger or smaller than the orange of F minus? Honestly, hard to tell. This is very hard to tell against this. However, they give us these numbers. Na plus has a diameter of 116. And F minus has a diameter of 119. Na plus is smaller. F minus is larger. Now I actually like this graphic better because it's also showing you that F neutral is smaller than F minus, O neutral is smaller than O minus, and it's showing you that Na neutral is larger than Na plus, Mg neutral is larger than Mg2 plus, and you can see how sodium is larger than magnesium is larger than aluminum, showing you effective nuclear charge and the change that you get with the ionic species. So I pulled up that graphic because I felt I had been mistaken, and actually we all learned something. Our rule held true. Fluoride is larger than neon is larger than sodium plus in that isoelectronic species. Great. Hooray. Okay. How do you feel on isoelectronic species? Ranking their sizes based on that. Good? There's one last concept in this periodic properties module, and it's all about how electrons come and go into these species. So I first want to show you this diagram. It's an energy diagram. Here we plot energy. We're going to be qualitative about this, not quantitative. So we don't need to give units for our energy. On the x-axis, we're going to show distance to nucleus. And we're showing the energy of an electron. This graph is going to come back in our next unit as well, so I'm introducing it now so that we see it again later. An electron has some energy when it's very far away from the nucleus. This is our ground state of the electron. But why do electrons want to be near atoms? They actually experience this grounding effect. They become more stable, lower energy, as they approach atoms, a nucleus, until they get too close, and then their energy skyrockets. The closer they get to a nucleus, the higher their energy. They actually have this sweet spot right here. So I want you to imagine two things. First, imagine that we take an electron and we put it into this energy well. What we're doing is giving an electron to a species. Does that process require energy or give off energy? The electron goes from a higher energy state to a lower energy state. We call that exothermic. When it goes from a high energy state to a low energy state. Loss of energy, exothermic. Loss of heat, loss of energy. What would be the opposite? Endothermic. And what would that process look like? Well, it would mean having an electron in a species already and taking it up and out of this energy well. This process is endothermic. Energy required. Energy put in. Endothermic, exothermic. Endo feels cold
Yeah.
because you are not part of the endothermic process. But endothermic to the system is getting warm. My coffee is going through an exothermic process right now, which is why it feels warm to me because it's losing heat. Actually, you cannot have endothermic without having exothermic. It's a trade-off. If something loses heat, something else is increasing in heat. So when we say that the electron going in towards an atom is exothermic, we're saying the surroundings feel heat because the electron is losing it. And for an electron to leave, we're saying it's endothermic because the surroundings have to give off heat for the electron to take that energy. So these two properties, electrons going in and electrons coming out, they're given two names. The first, and I'll try to keep this color coordinated. Actually, we're going to start with the second, so I'll keep it color coordinated. The black one is called ionization energy. Is this energy required or energy given off by the removal of an electron? That's right. We're looking at the removal of an electron. So this is energy required to remove an electron. What do you form if you remove an electron? A cation, I guess, if you're starting from a neutral species. So this process is neutral to cation. It requires energy. Which electron gets pulled off? The least stable? We're going to pull off first the most loosely bound. Maybe that means the least stable, the highest energy, the one that is furthest from the nucleus. So we're starting at high energy orbitals first, and then coming away. And we can actually do multiple ionizations. So we can call these IE1, IE2, IE3, etc. And the process is that it increases in energy. So IE1 is a lower energy than IE2. It requires more energy to pull the second electron away. What is an instance in which we need to pull one electron and then a second? Calcium to calcium plus. This we would call IE1. Some energy required to pluck out that electron. Calcium plus to calcium 2 plus, which is calcium's preferred state. That process is IE2. Which process requires the most energy? Calcium to calcium plus, or calcium plus to calcium 2 plus? Plus to 2 plus. I mean, imagine you're asking an already positively charged species to give up yet another electron. Is that going to be easier than taking an electron from a neutral species? No. That nucleus is now pulling on the remaining electrons even stronger. You've just increased its effective nuclear charge. So now it's going to be even more difficult to get that second electron out. So these values of IE1, IE2, always positive. Well, I'm not trying to show that as a positive charge. They're always positive energy values. It's going to require some energy plus this many joules. All right, here are some interesting trends that we find. As the radius increases, the ionization energy, the energy required, yeah? Is it easier to rip an electron off of francium or hydrogen? That francium has the same number of valence electrons as hydrogen, but francium's is in the 7s shell, the 7s orbital, very far away from the nucleus, severely shielded from the positive charge of the nucleus. That's going to be a lot easier to remove than a hydrogen electron that is right next to the nucleus. So how does ionization energy change? As the radius increases, the ionization energy decreases. Energy required gets smaller. We can give this example. Hydrogen to H plus versus francium to francium plus requires more energy for the hydrogen ionization. Larger IE. As the electron subshell increases in energy, how does the ionization energy change? For this, let's look at taking boron to boron plus versus beryllium to beryllium plus. We're not looking at necessarily the common ion they might form. Beryllium doesn't often form beryllium plus, it forms beryllium 2 plus. But we're just saying this first ionization energy. Which one is harder? What electron am I pulling out from boron? Pay attention to your periodic table. Anybody need another periodic table? I might have you do some more drawing on them today. You guys want to pass those around behind you? Who else? You pass some of those back. Pass some of those back. Anybody else? What is the electron configuration of boron? Did anybody not get one? Any extras? Did I do a perfect job? Except for one? There you go. I did a perfect job. Thank you, Mark. Saved my day. What is the electron configuration of boron? Ryan, you want to say it? Good. 1s2, 2s2, 2p1. What electron is boron losing? It's losing its 2p1. Because that is the highest energy electron, and we always pull out the most loosely bound electron. Okay. So 2p1 is being lost. What is beryllium losing? One of its two s2s. Which do you think is easier to pull off? Boron's 2p1 or beryllium's 2s2? As the electron shell increases, you're getting more loosely bound. It becomes easier to pull it off. Ionization energy decreases. Which one do I circle? Which one requires more energy to pull? Beryllium requires more energy, higher IE value. Why? Let's say it again. The S subshell is lower in energy, requires more energy to pull it out. The P subshell is higher in energy, requires less energy to pull it out. And we're pulling out the 2p1 electron versus one of the 2s2 electrons. So we're actually comparing P to S. Good. Now let's look at another trend. As electron subshells partially fill, ionization energy is going to shift. So I want to take an example here. If we look at oxygen to oxygen 2 plus, not oxygen 2 plus, oxygen plus, and we look at nitrogen to nitrogen plus, which of these will be easier to pull away? Well, we actually need to dig in more. This has an electron configuration 1s2, 2s2, 2p4, whereas nitrogen is 1s2, 2s2, 2p3. Is it pulling from a higher energy shell? No. But that's actually another way we could have said this. We could have said as shell energy increases, ionization energy decreases. Are we pulling from a different subshell? We're pulling an electron from the second shell, from the second p subshell, not the second p cell, from the 2p subshell. We're pulling an electron from the same shell and the same subshell. So this is not enough information for us. We need to transform this a little bit. Oxygen has 4 2p electrons. 1, 2, 3, 4. 1, 2, 3. That's nitrogen. 2p3. Okay, so we've got some terminology that maybe we need to clear up. Yeah? When we say partially fill, we should say beyond halfway. Once they get beyond halfway, what happens to the ionization energy? Which of these do you think will be harder to pull an electron from? Which of these do you think will be easier to pull an electron from? And you know that from the reading? Or you know that intuitively? Would you have added anything to that, Lizzie?
Nitrogen, like, it's half filled, it's pretty solid, it's stable there, it's chill. Whereas oxygen has the one extra third wheel of the party that just kind of needs to get out of the way.
Interesting. And oxygen is actually trying to get to an all singles party, not a third wheel removal situation. Good work. We've got this intrinsic stability from half-filled electron shells. So as we get more than half fill, as we partially fill these electrons, the ionization energy decreases. This is easier to pull away because it leaves behind a half-filled shell. This is harder to pull away. So which of these two options requires the most energy? Nitrogen to nitrogen plus requires more energy. So you are looking within a shell, or you're looking between shells, you're looking between subshells, and then you have to look within a subshell. How does ionization energy change as the shells change? How does ionization energy change as the subshells change? How does ionization energy change as the subshells partially fill? Okay? I do think that this one is the hardest to word. Do you guys agree with me that the wording is a bit challenging there? But visually, you can see it. This leaves behind a very stable orbital. This leaves behind a less stable orbital. More stable. Less stable. Harder to acquire. Any questions? All right. And we already looked at this type of scenario where we say, what is harder to do? Pull away an electron from a neutral species or an electron from a positive species. We know that those are increasing in energy with positive charge. Here's another tip that's good. Core electrons, much harder to remove than valence electrons. So this is similar to what we just looked at with the charges, but actually takes it a step further. We know from our calcium example that calcium plus to calcium 2 plus requires more energy. So we should be able to say that sodium plus to sodium 2 plus also requires more energy, correct? However, calcium plus to calcium 2 plus, IE1 to IE2, comparable, easy enough to do because calcium 2 plus forms readily. Sodium 2 plus requires removing a core electron. Now I'm going to say it doesn't happen, and this is maybe a bit of a lie, because you can get it to happen, but the energy difference, it's not comparable. The energy for Na plus to Na2 plus is not like the energy for calcium plus to calcium 2 plus. This requires removing a core electron. That's incredibly hard to do.
How do you know that it requires removing a core electron?
Ryan?
Because there's only one valence electron, so by moving one before to Na plus, you have to remove a different electron.
Na's in the first family, not the second.
Good. Na prefers to be Na plus, that removes a valence electron. Na plus to Na2 plus removes a core. Different from here, where calcium is in group 2, has 2 valence electrons, wants to remove both of them. Deal? All right. The flip side of all of this is called electron affinity, and it's a lot easier because because the trends are not as easy to predict. So you will see a lot of problems where you make predictions using these trends for ionization energy. But the reverse, adding an electron to a system, is called electron affinity. EA, it's in the game. I don't know about you guys, but these are terribly named. Ionization energy, what ion? Only cations. They should have called it cationization energy. Electron affinity, okay, I get it. You want to pull electrons towards you, but I could have also said, like, if I don't have a high electron affinity, you can take my electrons away. So this should have been called anionization energy. Like, just a small brainstorming session could have gotten them there sooner. This process is always exothermic. This is the energy given off by an atom accepting electrons. As we said, this is always an exothermic process. Electrons are falling down in energy when they come to an atom, but they don't all give off the same amount of energy. Here's one of our trends. Electron affinity increases when effective nuclear charge increases. You know what? We can write that better. We'll make it more like this. As the effective nuclear charge increases, electron affinity increases. Obviously, this is really only true for atoms in a row, because we know that the halogens all have the same effective nuclear charge. They will have different electron affinities. But for atoms in a row, we can say electron affinity increases with effective nuclear charge. They're pulling on the electrons more. They want it more. Beyond this, though, predictions are much harder. So you will need to make predictions with ionization energy. You will not have to make as many predictions with electron affinity. Why don't you guys take a break? Let's take 5 minutes to get up and move around. And we're going to move into Module 8 in Unit 4 after this. I want you guys to work on this one. The process corresponding to the electron affinity of S is which of these? I gotta say, Module 7 checkpoint, one of the most boring ones. It's like all drop down, just determining the relationships between stuff, trends. Does electron affinity make a species more negative or more positive? More negative. Electron affinity, it wants electrons for itself. So I need to take a species, a neutral or otherwise, and I need to give it electrons. So to show an equation for this, I need to have species plus electron becomes a more negative species. There are only two answers that show species plus electron. Species plus electron. Both of them are electron affinity equations. But only one of them is the electron affinity corresponding to that of S. Which one shows the electron affinity that S has? The last one or the second to last? Gabriel, what do you think? Is it worded strangely? Is it challenging to just figure out what it wants? Here's where they're trying to trick you. Is the process corresponding to the electron affinity of S forming sulfur or using sulfur to form something else? That's the question. But the process for sulfur's electron affinity is different. Sulfur's electron affinity is when sulfur takes electrons towards itself, not sulfur plus taking electrons towards itself. This is not the process of forming S, but the process of taking S through electron affinity and giving it an atom. Do you guys agree? We should be answering S plus electron to S minus. You might have also looked at this top one and said, well, that, is the ionization energy. All right. Now let's look at this. We've got in the same row, AS, SE, BR. Bromine, selenium, astatine, I think. That's a weird one. I don't like it. How does the electron affinity change here? Which one of these has the largest electron affinity? What's basically our one and only trend? As effective nuclear charge increases, the electron affinity increases. More energy is given off by that atom that pulls on electrons harder. How does, and by the way, this is across the row to the right. How does effective nuclear charge change? It increases across the row. So which one? Bromine. That's pretty much all I wanted you guys to see was how you're going to see those questions on RoChem. Any questions before we chug along into the next module?
So, doesn't electron affinity, it doesn't take energy, it releases energy.
Electron affinity releases energy.
So wouldn't the E be on the right side because it's releasing the electron?
It's not releasing electrons, it's releasing energy. Boom.
Yeah, the E is like, okay.
E minus is the electron.
That makes more sense.
Remember this graphic, electron comes into the atom, comes close to the nucleus.
It's like it releases energy, but why is the energy on the left side?
That's not energy, that's why. Good question. All right, ready? We have now finished Unit 3, which means we are that much closer to our Unit 3 to 5 module. Unit 3 to 5 unit test. It's coming up faster than I want it to. But we're actually on a good pace for getting ready for that unit test. So we're now on Unit 4, and we're going to dive into Module 8 on ionic and covalent bonding. Remember that you can find a document that has my expression of our learning objectives based on what I have in my notes on RealChem in the in the Unit 4 module on RealChem. Right at the top, it says Unit 4 Learning Objectives 1210, LO 1210. All right, so I want to start us off here by talking about chemical bonding in general. That's me. What? Oh, good. What is chemical bonding? Yeah. You know, I told you I was in that biology class for a visit last week. And one of the questions was, what type of chemical bonding is represented by this, like pointing at this arrow? And it was pointing at hydrogen bonding. We haven't talked about that yet. We will, though. And I want to say that might not be an appropriate label under chemical bonding. Chemical bonding is the force of attraction holding two or more atoms together. Attractive force holding atoms together. Well, atom has a requirement of two or more. Correct?
Dumb question, sorry.
That's okay. I do often say more than I write. I kind of do that intentionally because I don't want you guys spending too much time writing things. I want you to have the most condensed form of it. But there is a reason the lectures are recorded. So if you're like, he said more than that, I want to remember what he said, you can go back to get the longer version. Yeah. Your textbook and AI, they can also give you longer definitions than this. I'm actually trying to give you the most condensed version to make it as easy to copy down as possible. So, I mean, there is something to be said here. Hydrogen bonding is something that water experiences where an oxygen atom on one water molecule interacts with the hydrogen atom on another water molecule. And that is an attractive force, and it does hold those atoms towards each other, but it's very easily overcome. And so maybe this definition is too limited, holding atoms together. Maybe that's not defined well enough. We need to say holding atoms together with a minimum threshold energy of X. I don't know, but I'm not sure that I would say hydrogen bonding is, excuse me, a chemical bond. Because when you break a hydrogen bond, you don't change a chemical. But it's also not in the definition that you change a chemical when a bond is broken. Yes? 1610? It might be in there too.
It is, because I thought my brain we already went over
That's true. Yes.
So even though it's like a weaker force, then it's pretty hard-ish to break practically.
So it's if you're going to break a bond first, you're going to break a hydrogen bond before you break an ionic bond or a covalent bond. Those are the only bonds that I'm going to talk to you about. And this is funny, you know, the colleague that I was visiting in class, I mean, there were like 6 questions on chemistry all in a row. She said, John, what do you think? Am I doing a good job? You're putting me out of a job. You're teaching everything I teach from general chemistry to OChem. Why do I even have a class? Just go take bio. They'll tell you everything in the first 4 weeks, too. Blew my mind. And then, again, I was cringing at times because I was like, oh, well, that's one way to say it, but that's not how I would say it.
A lot of the chemistry that I've learned here is the exact same for, I've learned more chemistry in my biology class so far.
I know.
than my actual chemistry class.
It's odd. I mean,
It's just applied differently.
you do need chemistry to know biology. You can't get around it. You can't do biology without chemistry. You can, in theory, do physics without chemistry, but do you know what you're going to be working with? Matter. So that's chemistry. Technically, anytime you're doing physics, you are doing applied chemistry. Biology, applied chemistry. Engineering, applied chemistry. Medicine, applied chemistry. Congratulations, you're all chemists, just for being alive. These are our 2 main types of bonds, ionic and covalent. We've already introduced these a little bit. The brief background here is that ionic bonds form by transfer of electrons, and covalent bonds form through shared valence electrons, as the name implies. I hope you guys are okay with me abbreviating valence there, V-A-L. But can anybody remind us what valence electrons are? For main group elements, it's just the electrons in the outermost shell, S and P. Otherwise, for transition metals, it's the highest energy, S and D, or F as well. The names bond, ionic bond. I like my electrons taken, not shared. That meme is always so good. Shaken, not stirred. Instead, it's taken, not shared. These are our 2 groups. Why? Why do they bond? What's the point? What drives 2 atoms to transfer electrons between each other or share electrons? Cool.
They want to be, I guess, full outer valence shell.
Good. They want a full outer valence shell. Now that's true, but it doesn't actually give a reason why. Like, why have a full outer valence shell? A full outer valence shell has intrinsic stability, in the same way that we said a partially filled shell has intrinsic stability. So this is driven by stability of a full valence shell. That's it. Most people will just say fill the valence shell, which implies there's stability in having that. Okay, so when we talk about valence shells, there's 2 main families. The first period wants 2 electrons in its valence shell. So helium just wants 2 electrons. Hydrogen just wants 2 electrons. We say that these follow the duet rule. Hydrogen and helium want 2 electrons. And then to a different extent, so does lithium, and so does beryllium. Hydrogen wants to get 2 electrons around it. Helium wants to get 2 electrons around it. Lithium either has to work to get 7 additional electrons, or it can just give up 1 electron. And now it follows a duet rule. Its outermost shell is the first shell, and it has 2 electrons. Similarly, beryllium. These atoms are essentially just following the duet rule. Lithium and beryllium are different in that they can fill the second shell, but it takes a lot to do that. So, lithium and beryllium, are they in the first period? They're not, but they're close enough to the first period. That's where they'll get their stability from having a full valence shell. In the second period, and in all, I can't say all, in most main group elements. So we're just saying from row 2 and below. Main group, does that include the S block? Are these main group elements? They are. Group 1 and group 2, alkali, alkaline earth, metals, those are main group. Does it include the D block? Those are not main group. Does it include the F block? Those are not main group. Does it include the P block? Yes, these are all main group elements as well. S and P are the main block, the main group elements. So from our second row for the main group elements, an outermost shell includes S and P predominantly, which means that we're looking at 8 electrons in the valence shell. And this is our octet rule. Wait. Name me an element in the third period. Magnesium. Actually, let's go with a larger one. Let's say phosphorus. What is phosphorus's outermost shell? What is its valence shell, the number? 3. Not its valence electrons in the outermost shell, but what shell number is its valence shell? The third shell. How many electrons fit in the third shell? The third shell has an S subshell, that's 2 electrons, a P subshell, that's another 6 electrons, and a D subshell. The third shell is where the D subshell comes into play. And that fits how many electrons? 10. So how can I sit here and tell you that phosphorus wants to fill its outermost shell with 8 electrons when the third shell can fit 18? That's where I'm saying second group, second period, and those really do only have capacity for 8. Carbon, nitrogen, oxygen, fluorine, their outermost shell is capped at 8. But also most main group elements, they're not filling the d orbitals that are in their shell. They want to get to that noble gas configuration nearest to them. So they're actually just going to stop at S and P, not at their entire shell. But things like phosphorus, sulfur, bromine, xenon, they do have larger shells that are not completely filled. So this is why I'm labeling it this way. The second period and most main groups, they want to put 8 electrons in their valence shell. That may not actually be a full shell, but that is a full S and P subshell. Are you guys okay with this? That we say these atoms are going to follow the octet rule for the most part, but that kind of deviates from filling their outermost shell anyways? Or you're not okay with this? Think about argon. Argon is a noble gas, correct? We call it noble because it's inert. It doesn't drive reactivity. Does argon have a full outer shell? No. Argon has a filled 3s2, 3p6, 3d0. Argon does not have a filled outer shell. So these atoms, they're just trying to get to be like argon, who still has that intrinsic stability. Because if you give argon an electron, is it going to put it in 3d? Is it going to make 3d1? You give argon an electron and it becomes potassium 4s1. It doesn't even start to fill the 3d. So this is the odd part. We're aiming for the octet rule. We say this means a full outer shell, but actually it's more like a full S&P subshell for most of our main group elements. Okay? All right. That's just my, I don't know, that's my rant. It's just an oddity. That's all. Okay. So let's dive into ionic compounds a little bit more.
I'm sorry, can I ask, what about bromine?
What about bromine?
Doesn't it want 6?
Bromine doesn't want 6 electrons. No, it wants 8 in its outermost shell.
Am I crazy?
Bromine has 7 valence electrons, but bromine wants 8 valence electrons. Trust me. Oh, you're thinking of boron.
Is it?
Boron is actually, we'll come back to that. Not yet, but we'll
Okay.
come back to that later.
There was the funky one that doesn't follow the octet rule and wants 6.
Yeah, boron. We'll come back to it. All right, we're diving into ionic compounds. If this goes well, I'm going to be able to contrast it with our covalent compounds. So we'll keep things kind of paired between them. An atom with high electron affinity plus an atom with low ionization energy. These are typically what come together to give us our ions. We're going to rip an electron away, ionization energy, from something that doesn't require a lot to pull it away. And we're going to give that electron to an atom with high electron affinity, something that does really want that electron, gives off a lot of energy. The atom with high electron affinity is our anion, or becomes our anion. The atom with low ionization energy becomes our cation. And electrons flow this way. Correct? Atom with low ionization energy requires a little bit of energy to give away its electron and gives it to the atom with high electron affinity, which gives off energy once it accepts that electron. This is the process of forming our ions and forming our bonds. By the way, ionic compounds, this is going to feel strange. All ionic compounds are generally known as salts. So I know that you all think of a specific salt when you hear salt, but you've worked with different salts. When you salt your driveway, you may or may not be using sodium chloride. Oftentimes you're using magnesium chloride or other things. When they salt the road, they're not always using sodium chloride. So sodium chloride is a good example of a salt because it's an ionic compound. These ionic compounds are held by ionic attraction. This is like what we talked about on that first day. Positive charges and negative charges attract each other, the electromagnetic force. Oftentimes our salts are brittle, crystalline. They have high melting points and boiling points. And they have often good solubility in water. And because of that, are good at conducting electricity. Can you suppose why salts are crystalline and brittle? What makes them rigid? I would argue that it's this. We say that these ionic forces are isotropic. Iso there again meaning the same. Tropic referring to faces or directionality. So when we take a compound like NaCl, there are a few things that we're doing with this chemical formula. How do I want to say this? This is simply the lowest ratio of ions in a neutral combination. Correct? This is not a molecule. NaCl is not two atoms that exist together. NaCl is the lowest ratio of ions that balances each other's charges. But it's not just two atoms. Here is Na plus, and here is Cl minus. That's not a molecule. That's just their lowest ratio. And when these come together, they just continue to stack. Here's NaCl, here's NaCl, here's NaCl, here's NaCl, here's NaCl. This is all NaCl. This is why it's crystalline, because these forces are felt in all directions evenly. And I could show that up, down, left, and right, but it also goes backwards, and it also comes forwards. And you can see that a little bit better in this crystalline graphic. Yes, it does just end at some point. But NaCl is not just two atoms. It's not discrete. It's just the lowest ratio. You guys okay with that? And now because of that, this chloride ion, it's trapped, held by equal forces with all of these sodium ions around it. So it prefers this crystalline structure where all of the forces can be evenly distributed. And those forces are very strong. So if you want to try breaking this, you're going to get it to kind of crack apart. That's what we're talking about with it being brittle. It doesn't want to sever any of these bonds anywhere. So it's going to just crack. Does that feel okay? No? Yes? We're describing its properties, and we're just seeing how that compares with its structure here. Okay. This is something we've hinted at already, but the electronic structure of ions prefers to be like noble gases. So we know that calcium has an electron configuration argon plus its 3s2 valence electrons. What would you need to do to get calcium to just have a configuration of argon? Calcium 2 plus has an electron configuration argon. It's isoelectronic. When I say prefers to be like, we could say prefers to be isoelectronic with a noble gas. So tell me about chlorine then. What is the electron configuration? Use your periodic tables. And we can write the condensed form. What is the electron configuration for chlorine? Condensed, chlorine starts at neon. Neon, 3s2, 3p5. Is it really easier to get chlorine to be equal to neon's electron configuration? If we make this chloride, then once again, we have an electron configuration. Oh, I had a typo in my notes. Anybody catch that? It's around calcium. Calcium is in the 4th row. It should not be 3s2. Calcium should be argon 4s2. When we make chlorine chloride, now it has an electron configuration equal to that of argon. So we're not necessarily going to the most recent anymore. I don't want to make chlorine like neon and make it chlorine 6 plus, chlorine 7 plus, chlorine minus, much easier to form, gives it an electron configuration like a noble gas. Is this true for all ions? Because I said ions prefer to be like noble gases. Do all ions prefer to be like noble gases? Iron often takes on iron 2 plus and 3 plus. That's a loss of 1, 2 electrons or 3 electrons. Are those noble gases? No. So maybe I can rephrase this and say that the electronic structure of main group ions, not transition metal ions, not intertransition metal ions, just main group ions, typically prefer to be isoelectronic. All right. Actually, before I put this away, I need the board space. But this is a graphic very similar to what I had drawn on the board earlier. Do you remember? This is distance. Can't see it. This is internuclear distance. but it's basically how far apart are those nuclei together in their bonding. And as they get closer, they get this intrinsic stability. As they get too close, they destabilize again. So atoms, similar to their electrons, want to have this specific distance between them. I'm going to redraw this in a minute so that we can see it. This is for us to talk about covalent compounds. I can't show this as atoms with high electron affinity and atoms with low ionization energy. Instead, what we often see here is that we have atoms with similar ionization energies or similar electron affinities. That's to say, there's not one atom that is really good at giving up electrons and one atom that is really bad at giving up electrons. Instead, they both have a pull and a push on their electrons. So there's not going to be this easy win of one atom gives, one atom takes. Instead, they'll share. We can write this as a similar equation where we have two hydrogen atoms, and both of them have a 1s1 electron configuration. 2 electrons are coming in. And those two atoms can come together to form a molecule, H2. Both atoms now have an electron configuration that matches helium. Both atoms use both of the electrons. That's not to say there are 4 electrons. There are 2 electrons satisfying 2 atoms. Now they're both similar to helium. Similar to this, we're going to talk about their properties. These tend to be more malleable or softer. They have lower boiling points and melting points. So I want you to think about how salt, solid at room temperature, sugar, solid at room temperature. Salt is an ionic compound. Sugar is a covalent compound. Why are they both solids at room temperature? Well, they both have strong attractions for their like molecules. But when you put sugar on a hot pan on the stove, what does it do? It starts to melt and it turns into syrup. But when you put salt on a hot pan on a stove, what does it do? Nothing. Until you get it up to hundreds of degrees Celsius, and then it will start to melt. So when we say low melting points and boiling points, we're not saying that they're all liquid or gas at room temperature, but relative to our ionic compounds, they require much less heat. Many, not all, are insoluble in water, and even if they are soluble in water, they are bad conductors. We're actually going to come back in Unit 5 to talk more about solubility in water and conductivity of electricity. But here's where we're saying 2 classes of compounds, ionic which generally dissolve in water but have very strong forces between them, and covalent, which aren't always soluble in water but have much weaker forces between them. This covalent bond that holds them together it has this preferred length. This is another potential energy diagram. The only difference now is that last time we were saying, what if I had an electron and I brought it close to an atom? And now I'm saying, what if those electrons came with a whole other atom and they both got close to each other? So this is a small internuclear distance. This is if your atoms are overlapped very closely. A medium internuclear distance. And then we're saying, what if they are just separate? What if they never touched in the first place? So we can say, infinitely far away, their energy is going to just be some value. Here's where their energy will start. Just like our electron. Some distance away from the atom, our electron has some value. Some distance away from each other, these atoms have some value of energy. As they get closer, that energy decreases until it skyrockets again. And I'm not very happy with that shape, so I'm going to try and redraw it. Looks something like the one that we had on the board earlier, correct? It's got this dip. Why do atoms bond? It stabilizes them. There is an intrinsic stability between being bonded versus not being bonded. So, out here, is there a bond or is there not a bond? There is not a bond out here. So imagine that I come from out here and I bring it into this energy well. Am I releasing energy or requiring energy? Do you guys agree? Forming a bond releases energy. Yes? Look at the energy diagram. You don't have to wonder. Does it decrease in energy as they form a bond? Yeah. Is this endothermic or exothermic? Exothermic. Okay, what if I have a bond and I want to break it? Do you all feel confident on it? Go from the energy well, where there is a bond between them, and take it up out of that well. Does it require energy? Yeah. Breaking a bond, endothermic. Where do you think that energy comes from? Where can that energy come from to break a bond? Photons, great place. When photons hit the ozone layer, they break bonds between oxygen. Ozone absorbs the ultraviolet light, breaks some of its bonds apart. So it is absorbing the energy of the UV light, which doesn't permit the light into our lower atmosphere. That's the benefit of the ozone layer. It absorbs that energy because bond breaking is endothermic. You can do it through heat. How do you burn something in a fire? You just provide enough energy to it, enough heat. It's not the photons in a fire that are causing chemical combustion to occur, but there are a lot of bonds breaking in that process, and you just need heat to initiate it. But also, what does fire do? It breaks bonds. It also forms bonds. So burning something like that, burning something provides the heat to break a bond, and then it also forms new bonds, which releases more heat, which can be the heat needed to break other bonds, which will result in new bonds forming, which will release new heat, and that's the chain reaction that propagates through.
That's common when like with your, oh my gosh, experiment. You have your like 4 different. It has the energy to break the bond, and then it uses that extra energy to reform it.
I'm not quite sure what you're talking about. Next week,
Never mind.
we really didn't get to the end of Module 8, and I was really hoping to. So I'm going to move your homework. However, what's left is just talking about bond polarity, which is not incredibly hard. So I encourage you to take at least one stab at your Module 8 checkpoint and your Unit... Oh, yeah, take your Unit 3 checkpoint as well today. Next week, we'll pick up with polarity to wrap up Module 8. But we're going to use that to swing us right into Lewis structures, building the structure of a molecule. All right? Take care, guys. Have a great weekend.